mean, I regard this, for me, the main issue, all I really want out of this is that there are clear cases in science where probabilities aren't going to work. Now, exactly what does work, hell, I don't really care.
Yeah.
Whatever, I mean, I think the issue between us is one of underdetermination.
Right.
Both of these work insofar as we have constraints over what has to work. Both of them work. But you take different paths, and the question is, then I don't know.
Yeah.
I give up something, you give up something. What is done right or wrong?
Yeah.
So that's my view of it.
Yeah.
I don't know.
I agree.
Okay. All right. Good. It's a sensible view.
I've heard people.
The beauty of common sense.
Just nothing but common sense.
Yeah, the hat really.
I got a hat.
What are they gonna do?
Will disagree with me. Why do you make it?
I know, it's a good one.
This is coming. You and John will be indistinguishable.
Oh, what's that?
Why should I put a hat on?
Oh.
Just want to grow my hair out. So
You and I will be.
Let's get started. Let me remind you to sign in to for COVID for contact tracing. When you leave, just write your name, please. There is no talk on Friday because of the PSS. So many of us will be away during that day. The next talk is next week on Tuesday at 12:10, as usually. And Simon Dedeo from Carnegie Mellon University will be talking about consilience and epistemic values in the Royal Society. And you're all invited to come to listen to Simon's talk. They're always very enjoyable and very clever. So
In person?
it will be in person here. Yes, absolutely. It was a pleasure to Simon join us today. It's my great pleasure to introduce Matt Parker, who got his PhD from the University of Chicago. Matt works in a range of areas, in the field of science, probability, physics, with interest in mathematics, of course, and also somewhat in metaphysics, a little bit, right?
True. Guilty.
That's exactly what I meant, actually. So I'm glad you confirmed me. He is published widely on these issues in the European Journal of Philosophy of Science, in news, in studies, and he has a recent paper with John sitting here in Axiomatis. And he was recently associated with the project New Directions in the Philosophy of Cosmology, or in Cosmology at Western. And he's now visiting fellow at the center. And it's really a pleasure to have you. And today, I'll be talking about what counts as evidence in the vast universe. The floor is yours.
Thank you, Edouard. Okay, yes, so that's right. I was affiliated with Western and the New Directions in Philosophy of Cosmology project last year, last academic year. And what I want to talk about today is based partly on research and discussions there with Chris Smeek and Marie Guégan. Can you guys hear me all right? Is the level okay? Supported by Templeton. And of course, I've continued to work on this here at the center. So the usual preface, this is my own presentation. So credit to Chris and Marie for lots of good ideas. All blame on me for the things I'm getting wrong, as usual. This is Ziv. Ziv is a neuropsychologist. They have a theory that phenomenal experience X is caused by activity. I need to minimize something here so I can see my notes. Okay, hold on. Okay, there we go. It's caused by activity in brain structure Y. So that is, the theory is that phenomenal experience X is caused by activity in brain structure Y. So they conduct an experiment. Okay, now, it's not working, hold on.
I need to just get you back into the slides.
Yeah, thank you.
Okay.
So subjects are exposed to certain stimuli and ask certain questions while the brains are scanned. Ziv expects a correlation between the subject's answers and activity in brain structure Y. However, Ziv does not expect the correlation to be perfect. They predict a roughly 85% correlation between certain answers and observed brain activity. Ziv performs the experiment on 100 patients. To Ziv's delight, a 90% correlation is observed, better than expected. This seems to be strong confirmation for their theory. This is Nick. Nick is a very clever philosopher. He says Ziv is mistaken. Nick thinks that we might live in a very, very large universe, possibly infinite. And if it is large enough, he claims, then the fact that a 90% correlation was observed provides almost no confirmation for Ziv's theory. How can that be? Well, if the universe is big enough, Nick reasons, then this very same experiment has been or will be or is performed many, many times. Why is that? Well, you may be familiar with Borges's fictional Library of Babel. It contains every possible book of 410 pages with about 3,200 characters per page using a certain 25 symbols. Most of the books are nonsense, but among them is every story, essay, poem, and academic monograph that has ever been or could be written of a reasonable length. This is the Babel Image Archive. It's a real website that supposedly contains every image of 416 by 640 pixels with 4,096 possible colors. As with Borges's books, most of the images are just noise. But the library contains every possible image within those stated parameters. And that's more than enough that it contains pictures of just about everything you can imagine. It contains pictures of me and you, Ziv, and Nick. And it contains pictures of Ziv's experiment. Unlike Borges's library, it's searchable. We can upload a picture of Ziv's experiment, and the virtual librarian will tell us exactly where to find the best match for that image. And it gives you the address. This is abbreviated, but if you want the full address, it'll give it to you. You can copy it, go back to that same image whenever you want. It's there. Okay, but now suppose that instead of maintaining a library of all these images, we generate them randomly. For each pixel, we roll 4 10-sided dice to determine its color, and we repeat this until the image is complete. Then we repeat this whole process to generate another image, and another, and another. Eventually, just by chance, we will generate a picture of Ziv's experiment. But there are many different pictures of Ziv's experiment. There are pictures in various shades, tints, and degrees of clarity, pictures from different angles, pictures of Ziv conducting the experiment, and pictures of them calculating the results. There are pictures of them getting a 90% correlation, and 85%, and in other cases, 2%. If we generate enough random pictures, we will see pictures of the experiment producing every possible outcome. So Nick thinks the universe is a bit like this. Maybe it's not perfectly random. It's made up of particles or fields that obey certain laws. But the detailed configurations of the content seem to be partly random. And if they can be configured like Ziv's experiment here on Earth, they're almost certainly configured like Ziv's experiment elsewhere too. Furthermore, if the universe is big enough, then somewhere out there, they will be configured like Ziv's experiment, but with 100% correlation between Y activity and subject responses, and elsewhere with 50% correlation, and still elsewhere with no correlation. Every possible outcome of Ziv's experiment occurs somewhere if the universe is big enough. What is more, that's the case whether Ziv's theory is true or not. Ziv's experiment is vulnerable to statistical anomalies. Even if the theory is wrong, it's possible Ziv might get 85% correlation or better. So if the universe is big enough, someone somewhere will get a positive result. And even someone named Ziv, who looks like Ziv and is trying to test the same theory as Ziv, will get a strong positive result, whether the theory is true or not. Therefore, Nick reasons, the fact that a positive result was observed gives us no significant confirmation of the theory. So, if the universe really is so big, how can any observation be evidence for or against a theory? And how can we judge any evidence if we don't know how big the universe is? Cosmologists have been thinking about this sort of problem. Some think that we live in an infinite multiverse where not only is our own universe infinite in both space and time, but there are infinitely many such infinite universes, generated by a process called eternal inflation. And Nick presents his problem as a problem for cosmology especially. This is because if we have two different cosmological theories, and both predict that the universe is probably very, very big, then they both predict that just about everything will be observed somewhere. And so then it seems that no evidence could help us choose between the two theories. But as we've just seen, this is not just a problem for cosmological theories. It's also a problem for neuropsychological theories, and by the same sort of reasoning for theories of biology, economics, or physics. Any theory that requires empirical evidence is in trouble here. All empirical evidence might be worthless if the universe is big enough, and we think it might be. But fear not. Like any good advertiser, Nick has come to rescue us from a problem that we didn't know we had. All Ziv needs to do, according to Nick, is think about their evidence in a different way. They must understand the evidence not just as a 90% correlation was observed, but rather, I, Ziv, observed a 90% correlation, and I am a randomly chosen observer in the vast universe. That is, Ziv should represent their evidence in a first-person indexical form supplemented with a version of what Bostrom calls the self-sampling assumption. One should reason as if one were a random sample from the set of all observers in one's reference class. The very large universe, the 90% correlations Ziv observed, is almost certain to be observed somewhere, whether the theory is true or not. But if the theory is false, most observers performing the experiment will not observe that correlation. If a randomly chosen observer sees that correlation, that is evidence that a large portion of observers in the universe sees such a correlation. And that we can assume is very unlikely unless the theory is true. So if I, as a randomly chosen observer, see such a correlation, that should give me greater confidence in the theory. Hooray! Science is saved. Unfortunately, Nick's solution has a lot of problems. To begin with, there's the reference class problem. Ziv is supposed to be a randomly chosen observer in the vast universe. But what counts as an observer? Does it have to be human? Does it have to be intelligent? Should it be an individual organism or scientific community? Or perhaps an observer moment rather than a whole observer? What Ziv really wants to know is, given what they have seen or think they have seen, what is the universe probably like? Well, Ziv has seen a lot of things. Most of them are relevant to the question, does Y activity cause phenomenal experience X? So which observations and which observers are relevant to that question? Here's another problem. Nick's solution relies on a suspicious version of the principle of indifference. Consider this dungeon example. There's a dungeon with 100 cells, and each contains one prisoner. 90 cells are painted blue on the outside and 10 are painted red. Each prisoner is asked to guess whether they're in a red or blue cell. What is the chance that you're in a red one? Bostrom's self-sampling assumption seems to suggest that it is 1 in 10, or so he takes it. But that really depends on how your cell was chosen. If the warden just hates red and really has it in for you, maybe it's more likely to be red. If they use a pseudo-random number generator or 2 decahedral dice, it's probably blue. Who knows? The principle of indifference in one traditional version says that we should assign equal probability to each of the equally possible outcomes. But if that means that, given 100 possible outcomes, each has the same numerical probability, and each set of possible outcomes has a probability proportional to its size, that's surely wrong. Those probabilities depend on how the outcome is chosen. And even considering that we don't know how the outcome is chosen, it's hard to see what justifies a uniform probability distribution. So given a huge number of observers, which one is probably you? That depends on how you were chosen. Nick's solution assumes that each observer in the relevant reference class is equally likely to be you, and that's highly suspect. This is John.
Yeah, I'm smiling. The one you had of Nick, that was really.
Not as well. We're only flattering you here today, John.
I'm grateful, thank you.
John is also a very clever philosopher. John thinks that Nick is using the wrong sort of inductive logic. Nick tries to represent indifference as a uniform probability distribution, assigning the same small probability to each observer. John argues that what indifference really implies is evidential neutrality. And when it comes to some of these cosmological problems, many sets of outcomes get completely neutral support from the known facts and background assumptions. So instead of very small numerical probabilities for small sets and large ones for large sets, we get a non-additive inductive logic in which a large range of outcome sets are equally supported. I'm sympathetic to that point of view, but I don't think it helps Ziv very much. John's alternative inductive logic is predictably very weak. Now, instead of being an observer chosen according to a uniform probability, Ziv just has no idea who or where they might be. How then can they make use of this evidence that was bound to be observed by someone anyway? John has more to say about that, but let's continue with Nick's problems. We said that given a huge number of observers, which one is probably you depends on how you were chosen. But that raises another problem. You were not chosen. The premise that you or Ziv is a randomly chosen observer in the universe is flatly false. No god in the sky cranked a big tombola or threw a dart at the multiverse to choose which observer you would be. You are a product instead of your parents and the planet you live on. And Nick admits this. The assumption that you are randomly chosen is supposed to be a kind of heuristic metaphor. But then what exactly is this metaphor a metaphor for? And what justifies our relying on it? Next, Nick's solution implies absurd consequences like the doomsday argument. The Population Reference Bureau estimates that about 107 billion humans have ever lived. There are almost 8 billion alive today. So let's say you're roughly the 105 billionth person born. If births continue at the same rate per capita, there might be another 100 billion by 2050 and trillions by 2100. If you're a randomly selected observer among all those that have ever lived or ever will, what is the chance that you should be born among the first 105 billion on this planet? Very small, it seems, unless the number of future observers is very small. So the fact that you are only the 105 billionth person or so born on Earth is evidence So I'm trying to get to the scroll bar here. I don't see a scroll bar for the notes. Okay. There we go. So the fact that you're only the 105 billionth person born or so is evidence that humans will be wiped out very soon. Never mind how. Your mere position within the exploding proliferation of human observers is evidence that the end is nigh. But that's absurd. Whether humanity is annihilated tomorrow or goes on to colonize the galaxy, you're still only the 105 billionth human. That fact does not enable you to predict the fate of humanity. Yet, if you're a randomly selected observer, it apparently does. And that seems very wrong. So we have reason to doubt Nick's solution again. John again suggests that the doomsday argument is a consequence of using the wrong inductive logic. I'm not going to disagree, but as I will try to make clear, I don't think that's the only thing that's gone wrong here. I think Nick's solution is flawed even aside from that. There are other problems with Nick's solution, but the last one I'll mention today is a very big one. Infinitely big. Nick's solution supposes that if Ziv's theory is true, then most occurrences of their experiment will show a strong correlation and otherwise not. This presupposes some coherent notion of most. But the main reason for thinking the universe is probably very, very large was that many cosmologists think it's actually infinite. That is, there's many regions on the scale of our observable universe and as many observers as there are positive whole numbers. And if the universe contains a countable infinity of observers, then it's not at all clear what most observers means. Consider an analogy. Are most numbers prime? It would seem not. But that depends on the order in which we count the numbers. If we count in a special ordering, we can make it seem that 2/3 of numbers are prime. So then, how should we count observers in an infinite multiverse? This is connected with what cosmologists call the measure problem. Some think that problem is solvable, and others think it isn't, but there's no strong consensus on a solution. Nick Bostrom ignores this problem. He says that it simplifies things if we set aside complications arising from assigning probabilities over infinite domains. And it certainly does. It circumvents a big, serious problem. But the problem exists nonetheless, and scoping it out does not solve it. So Nick informs us of a problem that if the universe is big enough, all evidence seems to be uninformative. And then he offers us a solution that contains more problems. It's as if he enlightened us to the evils of morning breath and then sold us a mouthwash full of lead, arsenic, and radon gas. But fear not. Like any good advertiser, I have come to rescue you from a problem you didn't know you had, namely Nick. However, even though you may not have been aware of this problem or taken it seriously, a number of philosophers and cosmologists are and do, and they take up a similar approach to this and other problems, appealing to some version or relative of the self-sampling assumption. So it's a problem that needs attention. And the salve I'm selling is nothing more than some reassuring non-news. You don't have morning breath or dandruff or ring around the collar. You never did. Empirical evidence works just fine, no matter how big the universe is. The reason Nick thought that Ziv had a problem was that he got off on the wrong foot. Ziv expressed their evidence as a 90% correlation is observed. Nick took that to mean only that the experiment has been or will be or is conducted somewhere in the universe. And the result of a 90% correlation is observed somewhere in some instance. We could symbolize this using an existential quantifier as there exists something, little o, that is an observation of a 90% correlation in an execution of Ziv's experimental design. It's this existential quantifier that causes all the trouble. If the world is very, very large, then this existential proposition is very likely to be true, whether Ziv's theory is true or not. Nick's solution is that Ziv should take the relevant evidence to be not there exists an observation of a 90% correlation, but I observed a 90% correlation, and I am a randomly chosen observer. I think this still involves an implicit existential quantifier. We might write this new evidence as there exists a little o, which is an observation of a 90% correlation in an execution of Ziv's experiment. And I experience little o, and I am a randomly chosen observer. And perhaps we could formulate this in different, clearer ways. But as we saw, this new way of construing the evidence leads to many other problems anyway. These are the only two ways of construing the evidence that Nick considers. The first is obviously not good. The second also has problems, but that's better than an obvious failure. So it seems, to Nick at least, that the second way must be right. But this is a false dichotomy. No one has shown that these are the only two options. And I don't think that either is what Ziv really had in mind. Ziv says that a 90% correlation was observed. At face value, this could be taken as an existential claim. There was an observation of a 90% correlation. But I find it hard to believe that any scientist ever really took their evidence to take the form, someone somewhere did or will observe such and such result. If they have, they clearly shouldn't, as I think Bostrom rightly shows. I think what Ziv means to say is something more like this. My team recently performed the experiment, and in that particular instance of the experiment, a 90% correlation was observed. Now, the reference to my team here, I think, is inessential. It doesn't introduce any relevant self-locating uncertainty. It's just a way to pick out one particular instance of the experiment. The evidence, in other words, is that instance of the experiment, the particular one I'm talking about, resulted in a 9% correlation. Let big O denote Ziv's particular observation of that particular instance of the experiment. Then the form of the evidence I suggest is just big C of big O. Or in other words, that particular observation O was an observation of a 9% correlation in an execution of Ziv's experiment. How does this help? Well, Nick's complaint was that if the universe is very large, then it is almost certain that someone will observe this 90% correlation, whether Ziv's theory is true or not. But Ziv is on one particular planet conducting one particular instance of an experiment. If the universe is very large, does that make it likely that Ziv's particular instance of the experiment, the one they recently performed, should have exhibited a 90% correlation, even if the theory is false? No, of course not. The size of the universe has no bearing at all on how that particular instance should have turned out. Suppose Ziv is a Bayesian. That is, roughly speaking, they think that if some evidence E is more likely given a theory T is true than it would be unconditionally, and if E does turn out to be true, then you should raise your confidence in E in the proportions given by this theorem. This doesn't tell us how confident we should be in T. It only tells us how much more confident we should be than before, given how confident we are in other things. But Bayesians think that's enough. So can Bayesian Ziv make use of the evidence big C of big O to confirm or disconfirm their theory? Well, plausibly, Ziv does think that big C of big O was much more likely on their theory than it was unconditionally. So that result should significantly increase Ziv's confidence in their theory. Hooray! Science is saved. What if Ziv is not a Bayesian? For example, what if Ziv accepts John's material theory of induction? Or more to the point, what if that theory is the right, whether we know it or not? Well, that theory says that the correct inductive logic depends on the facts and background assumptions of the particular case. So perhaps the precise evidential relation between the observation and Ziv's theory is going to depend on details that I haven't specified in this toy example. But if the evidence just concerns that particular experiment, cosmic self-locating considerations shouldn't come into it. The solution I'm offering makes use of what philosophers of language call direct reference. But I don't think we need to worry much about how that works in this case. We only need to assume that we have some way of picking out a specific instance of an observation. To an extent, we can do that descriptively. The experiment performed by Ziv in Pittsburgh, we could refer to it as the experiment performed by Ziv in Pittsburgh on Earth on November 4th, 2021, in the morning, resulted in a correlation of 90%. But if that's going to get us out of Nick's woods, it cannot mean an experiment performed by someone called Ziv in a place called Pittsburgh on a planet that looks like Earth on a day that the local inhabitants refer to as November 4th, 2021. It has to mean really our Ziv in this city, on this planet, at that actual time, in this part of the multiverse. Otherwise, Nick will remind us that if the universe is big enough, there will almost certainly be many instances of the experiment meeting the description, all with different results regardless of whether Ziv's theory is true. So it seems we have to be able to pick out a specific instance, de re, if you will, in order to escape Nick's word. Now, John is one of the heroes of this story. Back in 2010, when he was the director of the center, he offered in a footnote a response to Nick very similar to what I'm offering today. He wrote this in the main body: I do not believe that the problem Bostrom outlines is a challenge to Bayesian analysis. And then the footnote goes on to explain. In brief, the Bayesian needs only that the poor theory makes the outcome of our instantiation of the experiment very unlikely, whereas the good theory makes it likely. These facts are deduced within the poor and the good theories, and no consideration of other observers who may perform the experiment is needed. And I've emphasized here the phrase our instantiation to highlight the focus on the individual instance of an observation, which I think is important here. So this is essentially the same solution I'm suggesting. And in part, I'm just repeating at greater length and volume something John already said, but with a couple of caveats. Firstly, I would suggest that the likelihoods cannot always be deduced directly from the theories in question. In fact, that seems to me rather rare. I think we have very few scientific theories that imply specific probabilities. Quantum mechanics, perhaps statistical mechanics, perhaps genetics, but a few others come to mind. Certainly, Ziv's theory does not. Their theory just says that a certain activity in brain structure Y causes phenomenal experience X, and specifies no specific probability. The uncertainties and the percentage correlation in Ziv's prediction come from bridge principles and auxiliary hypotheses, not the theory per se. Ziv knows something about how these sorts of experiments go and how reliable they are, and perhaps there's more judgment than calculation involved in the prediction. But exact calculations are not necessarily required for Ziv's experiment to be enlightening. For Bayesian Ziv, for example, it's only important that they, Ziv, think the evidence is more likely on Ziv's theory than unconditionally. Bayes' theorem then compels Ziv to raise their confidence in the theory, and that seems to be progress. Secondly, even though Bostrom makes use of a Bayesian analysis, I don't think that his challenge is really specific to Bayesianism. I don't see how any methodology or inductive logic can make much use of evidence that takes the form someone somewhere observes X, if indeed the universe is so very big. And I think Norton's defense here is not just a defense of Bayesianism. We can restore the power of evidence just by shifting away from these someone somewhere misconstruals to attend to specific instances of experiments and observations, whether the right logic is Bayesian or not. Bostrom and others instead shift their attention to self-locating considerations in order to derive useful predictions. John emphasizes how adopting the wrong inductive logic has led to absurdities when we engage in these self-locating considerations. I don't disagree, but I want to suggest that we should never have shifted our attention there in the first place. Unfortunately, many philosophers and cosmologists have continued to think along Nick's lines, or those of cosmologist Alexander Vilenkin's principle of mediocrity, that we think of ourselves as a civilization randomly picked in the meta-universe. They propose different ways of, in effect, counting observers or civilizations. They deduce different and often implausible consequences, debate, and continue the search. Even John himself, despite his footnote rebutting Nick, takes this up in a recent paper, Eternal Inflation Where Probabilities Fail. I think maybe we can take John in that paper, and I'm sure he'll clarify this later, to be assuming the principle of mediocrity hypothetically on the authority of cosmologists, and then arguing that if we accept that principle and take the approach it suggests, then certain things follow. In particular, he argues that the appropriate inductive logic in that context is his infinite lottery logic, very weak logic that does not conform to the standard probability axioms, makes very few meaningful predictions, and is of little use for confirming or disconfirming cosmological theories. I'm not going to argue with John today about the correctness of those conclusions. I only object to the premise. I think that the cosmologists, like Nick, have gone down the wrong road with the principle of mediocrity and similar ideas. We are not, after all, a randomly picked civilization, and thinking of ourselves that way leads to too many problems. But I don't think that confirmation of inflationary theories or other theories that predict very big universes is hopeless. As with Ziv's neuropsychological theory, it may be possible to construct theories that yield useful predictions about specific objects or instances of processes. In eternal inflation cosmology, for example, so-called pocket universes might be seeded with quantum fluctuations. Quantum fluctuations are governed by quantum mechanics, which in principle gives us well-defined probabilities for various events. Hence, given a sufficiently detailed quantum theory of how these bubble worlds are generated, we ought in principle to be able to derive well-defined probabilities that any particular pocket universe should have certain properties. And given that, we might also incorporate so-called anthropic considerations or observer selection effects by merely conditionalizing on what we know about our own pocket universe. We know, for example, that it contains human observers. So it seems we need to estimate the chance that this particular region of this particular pocket universe should have certain properties, given the chances intrinsic to the quantum processes that generated it, and conditional on the fact that it contains human observers and the conditions required for that. In principle, I think this could conceivably generate a prediction useful for testing the theory. I realize that I'm leaning heavily on this qualifier in principle. I know that cosmologists face great challenges in devising such a specific theory or deriving its implications. I'm not in a position to do that work. But in light of the foregoing discussion, such an approach oriented towards extracting predictions for our particular region from the stochastic processes that may have generated it seems to me more promising than, if you will, imagining ourselves as darts thrown at a map of the multiverse. Nick's worry about cosmological theories was this: if two such theories both predict that the universe is very large, then for any possible phenomenon, they both predict that it will be observed by some observer. But that should not necessarily trouble us. We might have two theories, T1 and T2, that both predict very large universes, even infinite multiverses, but T1 might predict that any particular region containing observers is most likely to have, say, a fine structure constant within a certain range, while T2 predicts that any particular region containing observers is most likely to have a fine structure constant within another range. Two such theories would therefore make different predictions about our particular region so that we can choose between them uncertainly, but more or less straightforwardly by measuring our own fine structure constant. In short, we do not need to imagine ourselves as randomly chosen observers in order to do science, neither in psychology, cosmology, or any other empirical science. We only need to refer our evidence to specific individual objects, processes, and experiments. Thank you.
A few minutes for a break, and then we'll have quite a bit of time for Q&A.
I'm gonna come in and say, some people and some people. I don't have anything to say. I'll just be saying.
But I will not. I should not.
Thank you very much.
I wanted to clarify.
Oh, good.
I know very much of some grad students walking around the streets on these days. In the past.
We've been for
Something that I become earlier, but I'm still reminded me of. Because of thinking of beauty problem, what was your analysis say for that situation?
Yeah. Well, you sure you don't want to save this for the Q? But yeah, I mean, I don't know. I don't have a solution to that problem. My sense is that that is a case where self-locating considerations are relevant. At face value, what I'm saying would seem to suggest that you should be a halfer, but I'm not a halfer.
We lose money if we're a hacker.
Yeah. Yeah. So I need to think more about how that problem fits with this, and also, likewise, Dr. Evil. That I think is a very different sort of case where self-locating uncertainties by the stipulations of the setup do make a difference. So.
Just a regular game where you made me realize that I never looked at something that should puzzle. So if we do things like medical diagnosis, I think prevalence data, something like that, space rate, rarity, before you go into the set, I say, well, my chance that you said, I'm doing just the prison setup.
Yeah.
And I'm like, so why is that a good inference?
Yeah.
Because I was not chosen at random for people.
Right.
But and yet I know that that's not enough inference that when I get the next piece of information. A lot of those cases. That maybe when I think that, then it sounds a little bit like a big it's something like you're acting like this stuff. Let me tell you what I did.
Yeah.
Then it might not be that you don't think it's maybe there's another reason why that didn't work.
Yeah.
But it seems like maybe it's like materially you notice that in some cases acting as this perform at the level of predictive performance. And it's especially got me puzzling to me.
Yeah. I think I have a little story to tell about why the as if sometimes works.
I would love to hear it.
All right, let's get started. If you're online and have a question, please write down your name in the Q&A box, and we'll bring you in person during the Q&A. John, and if you have a question, please raise your hand. John, why don't you start?
Thanks very much. That was great. Vastly more sympathetic than any other talk I've ever heard. But the stuff that you made me look smart. Thank you. Two remarks. You asked me in question time to comment on the endorsement of the principle of mediocrity. You construed it exactly correctly. The purpose of that paper was to say, is this infinite lottery logic one that is actually relevant to science? And so the purpose of the paper was to say, yes, I will take on the assumptions that the cosmologists are using, and then show you that if you follow those assumptions through, this is where you end up. I'm aware that those assumptions are contentious. It's not obvious to me that they're correct, but for my purposes, it doesn't really matter.
Right.
Second remark, you pointed out that if you apply the sort of logics that I favor in these cases, you don't get anything. I just want to say that's the way it should be. If Zib has absolutely no idea about where they are in the universe, then they don't know anything. And if the logic comes along and suddenly they know a lot, something's gone wrong.
Yes.
Right? Logic can't make you know things if you start out with complete ignorance. So I'm not afraid of logics that don't give you anything. I think that's the way it should be.
Right, exactly right. Yeah, I understand, I agree. And I have the only thing I would say to that is that yes, so that just shows more forcefully, even more forcefully, that if you're right about Bostrom using the wrong sort of logic, and instead he should use your sort of logic, then that just shows that his approach doesn't solve the problem, right? Because going to these self-locating considerations puts us in the context of a very weak inductive logic where we can't infer the kinds of things we want to infer. So Ziv still has a problem.
Yeah, okay, I'm happy with that. Yeah.
Maybe, great.
I find the response to the paradox aspect of this, the kind of invalidating of ordinary science, is deeply persuasive. I'm more concerned about whether this gives us the resources to handle actual probabilistic inference in cosmology. And I'm thinking in particular of the idea that this conditionalize on human observers and go from there. Because I worry that you get a repetition of the reference class problem there, and where we conditionalize on human observers rather than hominid observers or human observers in a solar system of 8 planets or human observers who speak English or human observers including David Wallace. I'm just not sure what those principal rules are there to pin down which group we should conditionalize on to get on to doing all this.
Yeah, okay, that's a very fair point. And I think I'm inclined to say that on one hand, I feel like we should conditionalize on more or less as much as we can, right? Obviously, we can't conditionalize on the value of the fine structure constant if we're trying to get a probabilistic prediction of what value we should observe. But if we're trying to get a probabilistic prediction of what value we should observe, I think we should conditionalize on all the other information that we have as much as possible. But I think in practical terms, it doesn't really matter because all that we can really usefully conditionalize on in that sort of case is that things are tuned in such a way that we have galaxies. And I don't think we can make much better. I don't think we can do much better to sort of analyze what conditions are necessary for humans to evolve as opposed to other conscious observers. I think that we're stuck with with a much rougher sort of proxy, like, is this sort of universe that's going to have a lot of baryonic matter that congeals into galaxies and stars and planets and is likely to give life to life.
I suppose the kind of thing I might be worried about is, I mean, let's suppose that sentient life is actually really unlikely to come about. So its likelihood of turning up, even in a universe as big as ours, is only like 1 in 1,000. Well, in that case, the likelihood of it turning up is going to be sensitively dependent on how big the universe is. The universe 1,000 times as big as ours is not likely. I mean, there's a sense in which all of this is a game as long as our grip of theories we're using is as tenuous as it is. But in principle, it sort of feels like we have to get quite lucky for the prediction to be robust against that sort of thing. And to some extent, it also feels like it runs into the sort of intuitive worry that doomsday argument base. It's like, yeah, how do we were doing cosmology, how do we suddenly get sidetracked by issues of evolution and almost a sense of fact let's change the subject or something.
Yeah, well, perhaps though, conditionalizing on the fact that we exist, if that leads us to conclude that the universe is likely very large, then maybe that's a valid inference. Maybe some version of a fine-tuning argument really does work in that sort of way. I don't know.
If it's the whole universe, sure, but we were talking of it's a bubble, I think. So it doesn't. I mean, it sort of feels like if there's infinitely many bubbles, then even small bubbles, there'll be infinitely many small bubbles of black holes, and infinitely many large bubbles of black holes. And then we seem to be back to sort of quasi-skeptical situations. It seems to be the inference that somehow we must be in a large bubble, even though they're just the same as small bubbles of black holes.
Yeah.
If it was the whole universe, I take the point.
Yeah.
If we don't know if the universe is big or small and conditional on being small, it's super unlikely we're here, then sure, I can see the case. But it's not so obvious I can do it for the public universe.
Okay, I think that's an interesting point. I'm not sure how to resolve it at this stage.
Siddharth, do you hear me? Yes, you do.
I do, yeah. It's kind of funny to see my own image put up on the screen like this. Yeah, thanks. My question was about, I just want to make sure I understand the response to the original puzzle. Is it a kind of, I guess my question is, how does the shift to the dere, so to speak, right, the insistence on this experiment in this context here right now, how does that solve the problem? Is it a kind of like Moorean insistence that I know I'm not a brain in a vat, I know I'm not a Boltzmann brain, and sure, there might be ungodly numbers of deluded people out there, but that's not me, and I just know that. Is it a similar kind of move that is being made here that resolves the paradox or not?
Well, I mean, I don't think that sort of the. I think that we might have to appeal to some confidence that, you know, I'm not a Boltzmann brain, but I think I can do that, as it seemed to have very good evidence moment to moment that I'm not. But I think that the kind of move that I'm suggesting here might be a little different. It's rather just to say that, look, if we just focus our attention on one particular outcome of an experiment or one particular observation, we might have a theory that predicts that for any given such observation, it's more likely to have such and such outcome rather than another. And then that just doesn't seem to be disturbed at all when we consider that there are other instances of the same experiment being conducted elsewhere. I don't know if that helps at all. Do you want to push it?
Yeah, so I guess the question would simply be that that's precisely what someone like Bostrom, at least in raising the initial puzzle, would deny, right? That the likelihood of seeing the evidence insensitive to whether or not the theory is true. But is your point that the shift to direct reference somehow makes that false? Because
yeah, I think that what Bostrom says is the likelihood of someone observing the evidence is insensitive to whether the theory is true or false. But I don't think he argues that in each particular instance, it's insensitive to whether the theory is true or false. And I don't think he can.
Okay, thanks. I'd have to think about that a little bit more.
Brian, do you hear me?
Oh, I'm supposed to repeat the questions. I forgot.
Well, I think that's fine for when they're asking online. Brian.
Oh, fair enough.
Yeah.
I can hear you. Can you hear me?
Yeah, we do.
Hi, Brian.
Okay. Hi, Matt. Sorry, I couldn't be there in person.
No worries.
So my question is a bit of a follow-up to what we were talking about the other day, but now I realize I have a different take on it. There was a part at which you said that this problem arises not just for Bayesians, and this is before the slide on the principle of mediocrity, but I don't think you need to go back to it if you don't want to. And I wonder if that's true. So if you're just using the law of likelihood and you treat the probabilities as the likelihoods as primitives, then I wonder if this isn't a problem if you're comparing the likelihood of one theory over another relative to some observation. Because basically at the end of the day, isn't Bostrom's point that if the probability of E is 1, then it's not going to confirm anything?
Yeah, that's right. But again, I think the problem is that the probability that so if the universe is large enough, then the probability that E is observed by someone somewhere is 1 or close to 1. And therefore, you've got two different theories. Against that background, they're both going to predict that the probability of someone somewhere observing E is close to 1. And therefore, the observation of E by someone somewhere doesn't do much to help us choose between the two theories.
Okay, so you'd still have to index it to particular individuals. Yeah, I think you're right.
Oh, good. Thank you.
Yeah, that was easy.
Thanks, Brian. Go ahead.
Right. I've got two questions. One sort of quite minor, but I'm just wondering about this argument of the existential quantifiers.
Yeah.
So it sounded like you were sort of saying, one claim is there exists someone who observes this house club, and then the other claim is this particular person observes it. And your claim was that second statement involves a hidden existential quantification. I'm just worried about that in the sense that, if that's true, sort of almost any statement in predicate logic would involve hidden existential quantification. If I say Casper is happy, you could say that's to say there exists someone who's happy who is identical with Casper. But to me, that sort of sounds like sort of make it too cheap to get. I don't know if that's sort of the reasoning you were applying.
Yeah. So I think I want to think more about how important the implicit existential quantifier is in Bostrom's solution. Maybe the real problem with it isn't that, right? So maybe the real problem with it has more to do with this idea of I am a randomly chosen observer, and how do we cash that out? Randomly chosen among what? Does it matter how many other observers are out there in the universe? Yeah, I'm not going to insist that the problem is that it can be formulated as an existential. But I do think that the right solution has to involve a reference that's not an existential. It has to be, indexable, this one right here. Does that help?
Yeah, that does. And then maybe the most important question is, you might think that there are situations in which the type of reasoning that leads to this paradox is legitimate, right? So, I might perform an experiment which is statistically significant, but it doesn't replicate. So, and you might want to say something like, well, humanity performed so many experiments over history, so sure we're going to expect some that are statistically significant, but don't give us any real results. So I'm just wondering, given your solution to the original paradox, can we still use that kind of reasoning to dismiss such results?
Yes, provided we have the additional results that show that the original one wasn't reproducible, right? So then we have a lot more evidence. And then, yeah, certainly, as we do science, we're going to expect fluke outcomes, and given the total evidence that we have, one individual positive outcome isn't necessarily strong evidence for any particular theory if we have additional evidence that says, well, that was just a fluke. Another way of putting it is that in certain ways, the import of the evidence does depend on how the evidence is chosen, right? So I wanted to resist Bostrom's idea that it really depends on me being a randomly chosen observer in the meta universe. But still, the import of my evidence does depend on how my evidence was chosen. So that, for example, if Ziv had run their experiment, the whole experiment with 100 subjects, 100 times with different subjects, and then ignores all the results except for the one that happens to confirm Ziv's theory or appear to, then that's choosing the evidence in a way that biases the outcome, right? So in a way, we have to choose. So we have to choose our evidence in a way that doesn't bias the outcome. But I just don't think that that means we have to think of ourselves as a randomly chosen observer among the actual observers in the universe.
Yeah, thanks.
Thanks. I think wondering whether this objection actually applies to the self-sampling thing. I'll just do it first in like the as a reductio of the claim that your evidence is like the magnificent conclusion. Totally. Fits with your argument. Like we don't need cosmologists to come along and tell us the universe is big. Something like some observer saw blah, that's inequality. Close your eyes at time zero, you're a Bayesian baby, you open them and you see something, maybe a hand, maybe a pen. You think, well, what's the chance that someone would have seen that somewhere? The universe is big, 1. The universe is small, very low. Probably wouldn't have been a hand or whatever. If you need cosmologists tell the universe is big, I thought that would apply to self-sampling assumption as well, just as another long list of problems, but now I'm less sure. It's right that there's going to play observers to see that sort of thing. I think it's not any more likely if I think the universe from randomly chose it. So the question sort of petered out. I was going to take it as like another argument. Worry for Boston, but no, I'm not sure.
Yeah, so it sounded to me at first like it's more grist for Bostrom's mill that that even your very first observation seems to confirm that the universe must be large. No, I'm having trouble thinking this through.
Well, sorry, I was thinking if that's a reductio to claim that our evidence is merely the existential claim. If it were, we would know, or it's very strong evidence, no matter what we saw.
Yeah, that's right.
That's clearly.
But then
What's going on is the existential quantifier is not a partition of possibility. So when you know you're going to update by conditioning on it, you basically told probability doesn't. You know, your expectation of your future credence doesn't equal your current credence. You're going to condition on
I think I just kind of lost your point there. Do you want to try again?
well, if insofar as we got into the puzzle by starting with the assumption that your evidence was existential,
Yeah.
then it's a reductio of that.
Yeah.
If it were, then we would know, or be very confident, no matter what we saw.
Yeah, fair enough. So, but then I think that's grist for Bostrom in the sense that, you know, he's also pointing out that the existential evidence isn't helpful, and then he just makes a certain move about what kind of evidence is helpful that I think is going the wrong direction.
I think I was initially thinking, oh, it's got an existential structure there, the same problem can apply, but then the fact that it's not quite the same form, maybe get on.
Okay, thank you.
I have some, yeah. I have a small question. I think. But now, I was wondering whether it makes any difference to the analysis if Ziv knows that there's all this possible, that all these actual Zivs, and that they could have been in the universe. They could have had the same experience without the theory being true. So if you are conditionalized not simply on her observation, but on her knowledge of and all the universe, whether it changes the analysis. And here somehow the gaining intuition is what it's a big bound country. Right? So I'm traveling in fake bound country. I see a facade. There's there are all the fake barns, there was other fake barns, all have been destroyed, but one, I see the fake barn, I see the facade, which turned out to be the only standing facade of a true fake barn. I come to believe it's a fake barn. Okay, that's evidence for believing that it's a fake barn. But if I know there's thousands of other observers near me who have the same experience as I do, as that, but they don't have fake bar behind the facade. It's just irrelevant to the justification I have for coming to believing that I've seen a fake bar. So just adding the knowledge that what I also could have seen if I happen to be in another universe. But does that change a little bit somehow your analysis?
Okay, I don't think I followed the example of are you saying a fake barn?
Yes, it's usually very similar to the one you described. Very similar to a word. You know the fake barn?
No, I don't.
That's right.
Sorry.
So there's this place in Pennsylvania where they have a lot of red barns.
Yeah.
And there was a hurricane. They've all been destroyed except one. Now you're traveling in there, and you happen to the first one you cross. And they build facades, right? There's no fake barn, but still the facade are standing. And you happen to travel through this county, and you come across a facade, and you find, oh, here's a red barn. But you're very lucky that's the only facade with a red barn. All the other facades are standing, but there's no red barn behind there. Now there are plenty of other travelers, just like you in fake barn county, right? And they all see the facade, and they come to believe, look, hey, here's a red barn. And but there's no red barn behind the facade. So it's a very similar situation, right? So all these observers, they all have the same evidence, right? In all the bubbles.
Yeah.
Right? They all have the same evidence. They all see the same facade. Now I see a facade and a red barn. So I'm in the world. My experience is connected to what is really the case. Now you could say, well, my evidence is the experience I have now. So you can make a very similar kind of argument to deal with a skeptical scenario, right? But of course, the worry is that once you know that you could have been one of the many other observers that are actually observing the same thing as you, and here I could have been, the prime who is actually in another bubble having the same evidence as I have now. Whether that knowledge, when I add it to what I know now, and then the correlation I've observed, changes the conclusion that should be drawn. So once you conditionize not simply on the evidence that you have, but on your knowledge that you have had other evidence because of the multiverse. Whether that additional knowledge changes the conclusion you should be drawing, it should be.
Well,
so that is second order knowledge, right? So second order, so knowing things about the kind of evidence you have. So I'm trying to complexify a little bit somehow the situation.
Yeah.
You've read Bostrom. You're very unlucky. You've read Bostrom. And when there's someone that destroys your knowledge, ignorance is bliss.
Well, look, I think that on Bostrom's presentation of the problem, being aware that the universe is very large definitely affects your analysis, right? And being aware that that there are all these other instances of observers, maybe instances of people very much like you that observe different results. That for Bostrom really does affect your analysis, assuming that you take your evidence to be of the form, someone observed this, right? In reality, of course, I don't think that matters, but importantly, I think that what matters here is not how many other observers there are out there. So for example, in the barn example, I don't think it matters how many other observers are out there observing the other barns, but if you know that there are a lot of other barns and most of them are just facades, then that should affect your analysis. And I think that this is a point that I might have liked to make about Bostrom's argument that I left out. In the dungeon example, Bostrom supposes that there's an observer in each dungeon, right? And so you think, well, I could be any of those observers. I don't know which observer I am. So the chance that I'm in a red cell is 1/10. What if there aren't any other observers in the other dungeons? Does that make any difference? No. Epistemically, you could still be in any one of those cells. Doesn't matter whether there's an observer there or not. So the real questions here, I think, are questions about epistemically, what sort of situation could we be in, or could I be in, not who could I be? And it doesn't depend on, in any way, I think, on how many actual observers are out there in the universe. What's really important in these analyses is what I know and what I don't know about what my situation is and what it could be.
No,
Is that-
there's a lot of people are still on the queue, so 30 minutes.
So I'm worried about this.
Okay.
I guess I don't know how big I think this universe has to be for this to be, this multiverse has to be for me to be worried about this. So to take an analogy, if I pull an image out of the Abelia library, or if I'm somewhere in Waterhead's library, I know not where, and you know, I get an image of John Norton. Right? It's in there somewhere, presumably.
Mhm,
Some
mhm.
way, this structure.
Yeah,
Or I pull the book off the shelf and it's John Norton's latest book, right?
Right.
So that's pretty amazing, right? And in either place now, there's some sort of shelving or indexing system. So I can I can add one to the URL, right? I can decode the way they've got the URL structured. I can look at the next image. And if it's another image of John Norton, I might even think that every image in this database is John Norton. But I also might notice that there's, you know, just one pixel getting changed each time. So I notice that there's some pattern to the way in which they're organized in this database. So maybe the whole thing is diagonalized in some cantor stack. Right? So eventually I figure out, oh, there's just everything here, right? But everything here is only once. But now I understand the pattern. I've learned something about I know something now that's independent of my status as an observer here, given the finitude of that database.
Okay.
Similarly, in the library, I might notice that one character has changed. So here's John's book with a typo. Here it is with another typo. Here, another typo.
That's the way.
Right.
Here's a copy with all the typos fixed.
Right. Now, if I have to get worried about the fact, though, that the pattern that I'm detecting might not be a real pattern in the cataloging or the indexing or the structure of the space that I'm in, right? It seems to me I've got to imagine that actually there's much more than just one copy of everything. There's a room where there's a room for every possible permutation of books in this set. And now the size has exploded. I don't even want to try to do the calculation in my head, right? Similarly for Babelia, they would have to have, like, you know, the next one isn't just if they actually stored all of the images, right? Rather than just having some random indexing scheme, right? Then you'd have to have one indexing scheme that goes through all the images in one order, one that goes through the next order, and so on. So what reason do I have to think that I can't find something out about the structure of this, the big set of books or this big set of images, if this is the right metaphor to be thinking about the inference problem here, in something that is of a certain size, but certainly not any bigger than that. And so what reason do I have to think that the universe is so big that I have to worry about there being multiple zibs all getting different results from their repeated sampling of the space, right?
Yeah. The only answer I can give you is that I think that the main reason you have for believing the universe is that big, and that you really would get, you know, multiple zibs and multiple experimental outcomes, is the assumption that it actually is infinite and somewhat random. Without that, then, I mean, I don't know of any other independent argument that it's not infinite, but it's so big. So this is actually one of the problems, I think, with Bostrom's original paper, is that he wants to be able to assume that the universe is as big as he likes, right? Big enough to even to contain really uncanny things just by chance. But I don't think he has any strong basis for assuming that, other than the hypothesis that the universe is literally infinite. So
What's the evidence?
Well, what is the evidence for that? What's that?
Eternal inflation.
Yeah, eternal inflation. So, I mean, yeah, it's a theory. So so we have this theory, cosmological theory that was developed to explain certain apparent coincidences in our own universe. And then when people try to model that cosmological theory, they find that generically the models generate an infinite multiverse of often spatially and temporally infinite bubble universes.
And that's the best supported that, or it's one we have to take seriously enough.
I think possibly that the degree to which that theory is taken seriously may be in decline, but I don't have my finger on the pulse of cosmology to that degree. On the other hand, what I will say is I don't think that we're going to be done with infinite multiverse theories anytime soon. You know, if it's not the cosmological multiverse, it's the Everettian multiverse, or say that again.
Very tame. Our infinity is a nicely measured from down.
Yes, true. So yeah.
Yeah, thank
Oh.
you, Matt. I want you to, like you could say more, things like that we mentioned briefly in the break, and to where your insight with kind of pre-existing understandings that many of us might bring to the table. And, right. One that we mentioned is, how should I take the lesson of rejecting self-locating probabilities here, to think about where in general we should apply them, because we know that there are places that reasons that they work, that you fully fleshed out the when is that appropriate. But the other one was think of the other half, which is within the principle of mediocrity, which is acting as if we're chosen. And noting that in even kind of straightforward diagnostic cases in medicine, we often act as if, right, if there's a kind of prevalence information in the background, particular disease, before I take a test, right, I'm going to act as if I'm a randomly chosen member of that population, and that will be my predicted probability for whether I have a condition. And I know that isn't actually what's going on. I'm not randomly chosen. Right? Part of people in this region, but somehow that assumption is at least at the level of predictive performance the right one to make that. And so you mentioned that you had thought through why that might be so, and how that would be appropriate there, but not appropriate here.
Well, I'm not sure I've really thought through that case. But what I'm inclined to say there is something like, we might just start from the fact that we don't have any particular reason to think, even if you're not randomly chosen, we may not have any reason to think that that as a sample you're biased, right? Or am I missing the point? Is this a case where we should think of you as a biased sample, but in a particular way, but nonetheless we don't?
I think it's very much analogous to the prison example you gave.
Yeah.
Right. If absent further information, I'm in a very similar situation. Let's say I know that in Allegheny County, here's the background rate, and I right before, and I think myself as a typical member of people in the county, right? I haven't taken above average risk behavior. I haven't done below average, risk behavior. I'm just looking at myself. The appropriate predictive probabilities is just the frequency of people who say I go for right now, right? Prior to taking a test, and being systematic, I carve out some reference class, and I make the as if assumption that I've randomly chosen.
Yeah.
Reference class. And that is the predictably correct procedure for that, even though there's no kind of explicit.
You mean it's effective?
That's right.
It's effective. It works.
And ubiquitously, when we're doing these inference problems, there's something like that going on, where there's an assumption which we can think of that's effective predictably, that has something like the logical character of I am
randomly
chosen, and then I'm assuming like a kind of earn model in which I select from,
yeah,
earn with that prevalence, and that's the effective procedure.
Yeah, Okay, so I don't know. I have kind of two thoughts about that. One is that it may be just sort of a kind of, it may be a case where the thinking of yourself as randomly selected is safe enough. You're not aware of any particular way in which the selection is biased. And now, of course, so for example, from John's point of view, that shouldn't necessarily mean that you assign a uniform probability distribution or assign the same probability to this individual as you would to, based on the statistics of the population, because you don't know if this individual is randomly chosen. But maybe it's just effective for practical purposes to do so anyway, and then update as you go. I also wanted to say something about why I think in some cases, thinking as if you're a randomly chosen sample might be helpful. And that is that, so suppose, okay, let's do it with Ziv's experiment. Suppose that Ziv's experiment has a certain chance of coming out this way or that. Each instance has a certain chance of coming out this way or that, in virtue of the fact that their theory really is true. Okay, so then given that, let's suppose Ziv conducts the experiment 1,000 times, and then let's suppose we choose one of those 1,000 instances at random, right? So I'm thinking like Bostrom, I'm a randomly chosen instance of an observer of this experiment. Well, in the finite case, we can sort of, we can use the expected chances of the outcomes individually to give us an expected distribution of outcomes over all the individuals. And then when we choose randomly from the individual instances, the outcome that we should expect to see in that case ought to reflect the underlying chances of the individual instances in the first place. And when I said that, Bostrom recognizes that we're not really randomly chosen and that this is a kind of heuristic metaphor. I think what it might be a metaphor for is that finite case where the outcome you should epistemically expect, whether you look at the individual case or first extract expectations for all of the finite number of instances and then choose randomly, those are going to coincide. You're going to get the same result. So in effect, I think that, in finitary cases, often thinking of yourself as a randomly selected observer, given that is effective, given that your expectations of what a randomly selected observer would see is informed by the nature of the process that's being performed. So when we go to the infinite case, then we get all kinds of problems. But I think that the metaphor of thinking of yourself as a randomly selected observer is ultimately really just a way of cashing out the assumption that the observation you're making isn't a statistically biased one, right? It's not something that's been chosen in a way that's going to bias the outcome. And therefore, we can just use sort of the intrinsic chances of the stochastic process involved to make reasonable predictions about what we're going to observe.
All right. With apologies for those who are still on the queue. We're gonna have to stop. Thank you very much.
Hooray, thank you. I've been trying to figure out how this plastic cover works, so thank you for this.
You got the whole afternoon to play with it and break it because it's not that robust.
Oh.
All right, so see you on Tuesday next week for Simon's talk.